of my last lecture. I hope we will finish in time. Let's try our best. Today I want to discuss with you this collective mode in the repulsive Fermi gas, which is called Landau zero sound. As I said, this repulsive Fermi gas at the excitations leaving very long, so practically collisional rate is negligible for the excitations close to the Fermi surface. So how then this collective mode is sort of made? So I remind you, this gas is described in terms of quasi-particles, which is particle plus cloud of created particle Hall excitations that move together. So therefore, this object has fermionic statistics in the first place, and second, it has some therefore effective mass, which is different from the mass of the bare particle, and they interact in a very strange form. I introduce you these Landau F functions, which in the simple form is just a G, our complete constant in the first order. In second order, it's more complicated functions of directions. You have much more interesting effects, but this I will leave for just for you. If you are interested, you can open the books, textbook and specialized books. So how we can describe this? I remind you, we have in a Fermi gas, so we have a field Fermi sphere, so now of quasi-particles. Let's talk about quasi-particles. So therefore, the things which we're interested in is if you are interested in low energy, large wavelength perturbations or collective modes, now we're interested in. So it is something which happens only at the Fermi surface, because it's only there you are allowed to make low energy excitations, etc., etc. So, but these particles or quasi-particles which are close to the Fermi surface, they have a very large momentum around P Fermi, a very high energy around epsilon Fermi. And you know from quantum mechanics, this type of description of this type of particles or objects is essentially semi-classical. So for this purpose, this simplifies quite a lot the description. Of course, the more sophisticated one would involve the green function, looking for the poles in the scattering amplitude and some channels, so you can make it a bit much more solid than what I'm now presenting you. But the description, therefore, can be done in terms of semi-classical distribution function. So that means you introduce some momentum distribution of particle, which is position and time dependent. What does it mean? You split your system in a very big boxes, let's say, of some size, which contains many particles in it, so you can define the distribution of momenta in this particular box, which is characterized by some R. And if it would be a good description in terms of collection of these boxes, where distribution function differs from space, and you have some time evolution than in time, if your wavelength of your excitation is much larger than this box. But typically when you're looking for the sound, that means long wave excitations, long wavelength excitations. So that would be an appropriate description. So now, of course, we'll be interested in small deformation. So we start with P Fermi minus P, step function. That was our zero, non-perturbed, which is now not position dependent at all. And then we add here, let me put here sigma, right? Because we have two components. So in that we write delta NP sigma, and this object, this guy, is now position and space dependent. So and the idea would be just to write the equation that describes the evolution of these things. And now, of course, if you have local distribution, semi-classical distribution, what you have to write down kinetic equation. And all semi-classical kinetic equations are built on the same principle. It's like Boltzmann equation for the classical gas, or now is equation for excitations in fermionic system or in bosonic system. The same. It has the same structure. Total derivative of this NP sigma RT, which involves the partial derivative plus derivative with respect to position times r dot, which is in our case is just velocity or p divided by m. In our case, it would be sufficient to have m because we are in the first order on the perturbation theory where m star is equals m. But generically, you can write here m star. Yeah, if you want to be more serious and take more sophisticated f function that we will take. Then, of course, you have the same term with a p, gradient with respect to p, and p sigma rt. And then we have p dot, which is force acting on a component sigma. And all this has to be equal to collisional term, which takes how many particles due to collision go outside, away from the state. This is a loss term. But also from the collisions of other particles, some of them can go back to this state, p. This is a gain term. So it's a gain minus loss. But important point that these things is proportional to 1 over tau, collisional rate of collisions between particles. And in our case, if we are very, very close to the Fermi surface, this goes to 0, so therefore we ignore. Yeah. In the standard kinetics, those who has kinetics, this is the dominant one. Yeah, this is, they start, if something named Chapman and Enskog tells you, this is where they start. So this term gives you local equilibrium with local temperature, momentum, etc. And then this part generates all the kinetic, so time derivative and spatial derivative. But in our case, we set it to 0. So the question is, of course, with this we have no problem. What is this one? How we can define f? Now we have this definition of, remind you, the definition of the change of the quasi-particle energy if you change your distribution, because it's exactly what happens here. We change our distribution. So therefore, the change of quasi-particles energy, which is one of the volumes over p prime sigma prime, here comes Landau f function p sigma p prime sigma prime, and then we have delta n p prime sigma prime. If this is position dependent, then this is also position dependent. And we know if the energy of particle depends on positions, looks like potential energy, we generate a force. So therefore, our force, F sigma, would be simply minus gradient, spatial gradient of delta epsilon p sigma. And in our case, this becomes extremely simple, because we know that F is just G. So therefore, I have G divided by volume. And then it's only plus and minus component. Yes. So for plus here, so let me write it like this. Minus sigma. P prime minus sigma. It's exactly this term. Remember, we have this epsilon p. Sigma in the first order was just epsilon p plus g n minus sigma. Remember this. So therefore, if these things change in space, this is also space dependent, and this looks like mean field potential energy. When it is position dependent, the particle experiences force. That's exactly the force that we need here. And sorry, I forget here minus and a gradient, spatial gradient. Oh, no, not here, sorry. So now the force would be therefore minus g over volume, sum over p prime, and then we have delta n p prime minus sigma. This is our force. So of course we now want to simplify it a bit, because we of course consider this delta n p prime sigma is small, so slightly vary your distribution density. So distribution, local distribution here. So this delta n p sigma. So therefore we linearize our equation, because here you see you have some sort of nonlinear term here, because this contains delta n, this contains. So let's linearize this equation. So here, this one, d dt, this is position and space independent. So therefore, time derivative, partial time derivative, and a gradient in space acts only on here. Yeah, so they write simply d dt, and then plus p over m gradient r. This acts on delta n p sigma rt. This is these two terms. So here, f, as I said, we have to write, therefore, minus g over volume, sum over p prime, and then we have delta n p prime minus sigma. That is our force. But now here we will have gradient on p acting on our step function. This is our non-perturbed distribution plus delta n p sigma. And because we have now here delta n in a linearized form, we can ignore these things.
Shouldn't there be now a gradient to the expression for f sigma, like the lowest?
Yes, so, okay. I put it here, but again, I forgot it here. Yes. And here must be gradient again. Yeah. Yeah. So now, therefore, on a linearized level, I have here delta n, so this I ignore. So I end up here, and this all has to be 0. Yeah. So therefore, I have only to calculate these things. And remember, you know, in this, when you study electrodynamics, if you take a gradient of the function that depends on modulus r, what it is r over r f prime of r. Yeah. So therefore, it's the same rules in here. So these things is EP, and then minus delta function pf minus p or p minus pf. Now it doesn't matter. Because the derivative of the step function, it goes like, for smaller, it's 1. For larger, is 0. So it's minus delta function. And EP, I will use all this notation. Let me write here. EP is just p divided by p. It's the direction of p. Yeah. So finally, what I get here would be equation that I get would look like this: d over dt plus p over m gradient r acting delta n p sigma. Then I will have this plus should I write delta p minus pf. Then I will have g over volume sum over p prime. And now I will have EP, or maybe I should write EP outside. EP, that's not confusing. And then I will have sum over p prime. And here I will have gradient over r, delta n p prime minus sigma. And it also depends r and t. Yeah? Just put it here. And it all equals 0. And here also r and t. So now we have to solve this nice equation. And of course, for the solution, I will use the following ansatz. Delta n p sigma of rt is, I just put some amplitude. So first of all, you have here delta function. Here you have an integral or sum. I just write delta function p minus pf. So that means this change in delta n appears only at the Fermi surface. Then I will write some amplitude, kappa, that depends only on the direction of momenta p on your Fermi surface, because modulus is fixed by pf. And then I write a plane wave, e to the exp I k r minus omega t. It's a plane wave, yeah, with a wave vector k and omega. Yeah. So now I put it in there, in this ansatz. You see I will have here delta function, which cancels my delta functions. Plane wave, it's nice property. So here it simply gives me ik in a plane wave, because I sum over p prime. And p prime here is only here and here. Yeah? And here also it gives me minus I omega. This gives me ik, and again exponent. So that means exponent and delta function cancels. So what I get would be just an equation for my amplitude kappa. sorry, these long formulas I don't want to write. Yeah, but believe me. So finally, if I put this ansatz in here, what you get would be the following: omega minus V Fermi, yeah, because here P, but my ansatz fixed my P to P Fermi, yeah, so therefore, and then P Fermi divided by M is just my V Fermi, and then you have K that comes from the gradient, and then you have EP, it's the direction of this P, yeah, so it's a dot product, all X kappa EP. Yeah, that's what is left from here. Would I cancel the delta function, the plane wave? And now from there, I put it on the right-hand side. And then you will have G, K, EP. Yeah, EP was in here. And K comes from this gradient. So K, EP. And then I will have integral dP prime. That's my sum over K prime, over P prime. Then I will have delta P minus PF. That's from my ansatz that I have to put in here. And then I will have kappa E P prime. Yeah. And if you write these things carefully, yeah, you see angle you cannot integrate out, so in principle, because you have direct dependence on direction here. So the angle integral remains. But over modulus, you can integrate. So P squared dP with this delta function gives simply P Fermi squared. Yeah? And then if you arrange these things, so what you get here is the following. You will get F, V Fermi, K EP, and then integral over direction of EP prime over 4 pi times kappa EP prime. F, I remind you, F was our G density at the Fermi surface, or 2 AP Fermi over pi h bar. Yeah? You see, you will get here P Fermi squared. 1 P Fermi I took here, yeah, to form the density of states. Here, and this form a density of states. And then also I have to multiply by M, and I divide by M, and the rest P Fermi divided by M is just V Fermi. So you can just check. Yeah? So now we have equations like this. This is the left-hand side, and this is the right-hand side. Yeah? So this equation is very easy to solve. Yeah? You divide by these things. Yeah? Let me write it here. To have a kappa EP equals F, then you have V Fermi K EP divided by omega minus V Fermi K EP, and integral d omega EP prime 4 pi kappa EP prime. So this equation is very easy to solve, yeah? Because here there is nothing, you see, it's just a number. So what you have to do, you just integrate over EP divided by 4 pi, left and right hand side. That on the left, you will have exactly the same integral, exactly the same number. Yeah, and if it's non-zero, you cancel, but of course we're interested in the case where it's non-zero. So what is left, yeah, is just equation like this. 1 over F, let me divide it, integral over d omega EP over 4 pi, and this expression, V Fermi K EP divided by omega minus V Fermi K EP. And this determines you the relation between omega and K. That's what we want. Yeah? And to calculate this integral, of course, we have to choose in the direction in the EP. There you have to choose the spherical coordinates where the K is here, yeah, K EP, EP is somewhere here, unit vector, and this is theta, and this is phi. Yeah. And therefore, phi, there is no dependence, so it depends on the cosinus. So you just continue, it will be 2 pi over 4 pi. The 2 pi is integral over this angle. And for the cosinus, we will have sinus theta d theta from 0 to pi. And here we will have v Fermi k cosinus theta, omega minus v Fermi k cosinus theta. This integral we can easily calculate. By just introducing, you see, sinus theta d theta is this minus d on cosinus theta, so it becomes algebraic integral. And if I introduce, if I write omega SS, which is unknown, v Fermi times k, yeah, so therefore this goes away, this goes away, and here we will have simply S minus, would be integral like this. You perform this integration and you get the following answer, that 1 over f equals minus 1 plus s over 2 log s plus 1 divided by s minus 1. So this is the equation of s. In other words, this is the equation of the speed of this strange sound. Yeah? S v Fermi is a speed. And you see, f, we know, this is a small quantity. We are in a weakly interacting regime. So therefore, 1 over s is a large. Of course, you cannot solve it generically, only on computer. But for very small f, so that means very large, 1 over f, you can find an easier solution, approximate solution, noting that if s is slightly larger than 1, so here we'll have roughly 2, here we'll have 1/2, but here we'll have a small number. So I have a log of a big number, which is also big. So I can balance large left-hand side, and therefore, in this case, large right-hand side. So making long story short, the answer is S equals 1 plus 2 e to the minus 2 over f, approximate. This is, of course, true for f much smaller than 1. Yes? Because you see, there was here omega, and if I put omega in the form S times k Fermi, so V Fermi k, yeah, you see that V Fermi k I can cancel everywhere. So there was here V Fermi k, and here omega, which I just put S times V Fermi k, and V Fermi k was here also.
I was thinking about this K.
Which one?
K. Kappa, or I don't know. The first one.
I choose the polar angle. In integration of a direction of p prime, EP prime, I choose the special coordinates such that the z-axis is along the k. Yeah? Then, of course, k dot EP prime then would be just the cosinus of this angle. And there would be no dependence on phi. Yeah? So, you see, we find that indeed we do have a wave sound-like excitations here, even if we completely neglect collisions between quasi-particles. Important also that the S is larger than 1, but I don't want to spend time now. If you're interested in this makes this actually stable. This thing is important. This is stable excitation. So that means it doesn't have a priori imaginary part. And this is important that the velocity is above V Fermi. You can ask me afterwards, why is this? But I don't want to spend time now. Just want to stress the last few sentences concerning this Landau zero sound. You see, this is not thermodynamic sound, because if you calculate the velocity of thermodynamic sound, which is square root of 1 over m dp dn, yeah? Remember, we have this p, 2phi for the epsilon n and plus Fermi. You will get V Fermi over square root of 3. Just easy calculations. Yeah? you get it like this. And you see this is clearly different. Yeah? Clearly different. So it's not at all thermodynamic sound, as we know already, because we completely ignore collisions. It is coherent motion of the particle Hall excitations. And if I look how it looks like, this is my Fermi sphere. If you look at this one, you see this is a number. This is very close to V Fermi K. So what you have is, if this is the direction of K, propagation of my wave, then here I will have a plus peak, very high peak of, let's say, and here I will have a very smooth deficit. So this is a deficit of the, and this alternate like a wave in space. Yeah? So it's very asymmetric change in my quasi-particle local distributions. Yeah? And indeed, you need to go to the quasi-particle distribution to describe this sound. It's not enough to think in terms of density, pressure, like what we always do if we consider thermodynamical sound. So it's a very specific excitation, yeah, which is sound, but it's very often called either Landau high frequency sound, yeah, because in this case, it is actually, we ignore collisions, yeah, 1 over tau. And typically here you see you have terms of the order omega. Yeah? So this means that we are in the regime omega tau much larger than 1. So it's completely opposite to the hydrodynamical regime. So therefore, these formulas requires high, this is very often called high frequency sound. Because you need this condition to ignore the collisions. If you want to be fair, just include them, but this would create the decay, etc., etc. So I finish with now repulsive Fermi gas. So now a short break. Matilda will make some announcement. And then we now continue with the attractive Fermi gas. Yeah? Yeah. Yes.
So could you please get more into detail how, or what is the reason for the step? Because in the next equation there is no chi anymore. So how do you get rid of this function so that you don't know? What's the logic behind that?
And I cancel this. Because I integrate over, I can call it whatever you like.
Yeah, and the integral on the right-hand side does not depend on the speed of the solution.
And then you get, when you cancel, I divide by 1 over f, that what is remains, this cancels to this. I divide, so initially would be like this. No. If technical question, maybe ask afterwards. Yeah? Okay. Yeah?
What's like a physical system where you could see that zero sound?
Helium-free. There you can have even more. It's a more complicated system. There you can have different branches. Sorry, I didn't mention here, for the lack of hurry, that in this case you can only have where these things are in phase. They are only in phase. And that's the only mode that can exist in this weakly interacting regime. In helium, you can have also spin waves. These are different. So you generate a misbalance between plus and minus. But this typically requires a threshold. So the interaction, the component of the Landau wave function must be stronger than something. OK, so now announcement. And I will use time to clean the blackboard.
So for those who are not used to hiking in mountains, so be aware that this is not necessarily safe. So please check your path, check the weather, take a map. If you have maps at the secretariat, and you can make a cut go back to les Hooch by bus. If you have any trouble, I give you my phone number. So of course, if you have trouble, if you are stuck somewhere, please leave it. But of course, this is not a taxi phone number. Just in case you have any troubles. Second announcement, I go to the drugstore this afternoon to les Hooch with Alberto. So if you need to go to the drugstore, I still have room for three other persons. So if you are interested, we meet at the car park at 2:25.
Okay, so
1 hour.
and 5 minutes. Okay, let's now, that was a repulsive gas, yeah? On a single particle level, it's very similar to just ideal gas. You have a single particle electron hole excitations with some effective mass. And the repulsive case have a collective mode Landau zero sum. And it's all based on assumption that there is one-to-one correspondence between the states of ideal, at least in a single particle level. There is a correspondence between ideal Fermi gas and interacting Fermi gas, one-to-one correspondence, which is not the case for the attractive interaction. In this case, you will see attractive Fermi gas. In this case, you will see that the ground state T0 will have completely different structure, and the BCS pairing occurs. Of course, it's all theory starts with the experimental discovery of superconductivity in metals, and it was kind of very simple idea. Okay, how the fermionic system can be superconducting. So, well, the fermions can simply form a two-fermionic bound state, and this is bosons, and these bosons can superfluid, behave in a superfluid manner. But then, of course, you think, what is the attractive interaction in metal? Okay, this is exchange of the phonons that could generate an attractive interaction. The problem is, of course, this is a particular metallic problem, how these can overcome the repulsive Coulomb, which is very strong. But in cold atoms, there is no repulsive. Let's forget about this story. But how this attractive interaction is weak. And we know in 3 dimensions, to form a bound state, you need a threshold. Attractive interaction must be strong enough to form a bound state. Otherwise, it cannot be formed. Yeah, and the electron-phonon interaction is actually weak. Yeah, and it cannot form a bound state if you naively put it into the just a 3-dimensional case. So what was the resolution? The resolution came actually from a very nice idea of Cooper, and what I want to discuss, he considered a very simplified problem or model, Cooper problem. He just said, okay, electrons in metal, they're not like free particles, so they have this Fermi sphere. Yeah? So with a part of the space is blocked for the electrons. So they cannot go there because it's occupied, and it requires a huge energy to kick them out, get in. So what he considered a very simple model, which is of course very much artificial. He considered a motion of 2 particles. It's actually 2-particle problem. But not in a free space. We know it's a Schrödinger equation. But in the presence, so this is P, this is minus P, yeah, such that the center of mass is 0, yeah, momentum center of mass is 0. But he said, this is my frozen Fermi sphere, so that means these states inside the P Fermi not available. This is my model. They are not available. Yeah, frozen Fermi sphere. So the only available states for my particles, because they would interact, they would scatter, it's only P larger than P Fermi. So the Hamiltonian, therefore, is minus h bar squared over 2m, Laplacian for the first particle plus Laplacian for the second particle plus interparticle interaction. Yeah, that's my Hamiltonian for 2-particle case. But the wave function, R1, R2, he writes in the following form. Okay, we expand in plane waves. Yeah, sum over P, but now P larger than PF. And it's exactly why because these states are not available. So here, these two cannot have only momenta above. And then you write some coefficient Cp, and then you write I over h bar, P, R1 minus R2. Yeah? This is center of mass. Center of mass. It's the most favorable case for the forming a bound state. Yeah? Of course, for free particles, when you have no V, R1 minus R2, then the energy of two particles has to be larger or equal to epsilon Fermi, right? Because the particles can be only above P Fermi. So now let's switch on interaction, see what happens. Huh? So we use this ansatz for the wave function. They put it in this equation, and then after some multiplying and integration with the plane wave integrating over space, etc., we come to the equation for the amplitude Cp. And this equation looks like this. 2 epsilon p, clear, it's from this and from this. Yeah? Laplacian acting on this wave function gives you p squared over 2m. Yeah, it's epsilon p, but you have 2 plus. Now you have part that comes from the convolution, so it's a product of this wave function to this, and then you go to momentum space, that would be convolution. 1 over volume, sum over q, larger than pf. And here you will have v of p minus q, cq, equals E times Cp. And here again, P is larger than Pf. Or you can write larger or equal, it doesn't really matter. So sorry for skipping technical details, just believe me. So product of two functions in positional space, in momentum space, will be convolution, which is written here. Okay, so I can write the following. Let me take this term in here, this term on the right-hand side, and then divide and multiply it. Sorry, I forgot Cp here, sorry. Then this term together would be something which contains Cp. So I can write it like this. Therefore, Cp would be equal minus 1 over 2 epsilon p minus e. Yeah, recognize 2 epsilon p minus e, that it comes in here. And minus, because this term goes to the right, 1 over the volume, sum over q larger than p Fermi, and now v of p minus q, cq. So this is equation. Of course, this is as complicated as the initial one, because I don't know what is v p minus q. But then he used model form for the interaction. So he said, and this is actually modified, mediated by what people know about the electron-phonon interaction. This is, of course, very model. So this is a very convenient model to solve this equation. So he said it is minus, so it is some, it's called v, 0, or maybe let's call it g. Yeah? G, which is negative. Yeah, let me write it like this. Huh? When both epsilon p and epsilon q, yeah, we have here p and q, are larger or equal than epsilon Fermi, or smaller and equal than epsilon Fermi plus omega 0. Omega 0 is some energy scale that, of course, in the metals it's sort of dBi frequency. I skip h bar. And of course, we assume that omega 0 is much smaller than epsilon Fermi. Then becomes calculations become extremely simple. And 0 otherwise. So when either p or q or both is outside this range, interaction is 0. Don't try to write this in a positional space. That would be a horrible thing. Yeah? Don't try. Yeah? And it's none of the real interaction can be similar like this. But it's a convenient model. It's many-body system. And it's our model. We want to do what we want, as long as we get some meaningful results. Okay. So now can we, how we simplify? So that means that my p and q should belongs to p and q should belongs to some region M, yeah, which is it starts from P Fermi. Yeah, it's here. Up to P Fermi, square root of 1 plus omega 0 over epsilon Fermi. That's this region. That's exactly when the omegas, epsilons, P squared over 2m belongs to this region. It's exactly when the amplitude P and Q belongs to the same region. So it's the same. Yeah? So therefore, how does it help us? It helps us in the following way. So Cp is 0 if P does not belong to M. Yeah, clear? Because the right-hand side then 0, so we get here 0. And if P belongs to M, Cp equals, let me put it in here, it's minus G, that's my interaction, divided by 2EP minus E, and now I have sum over Q belonging to M, yeah, because I sum over Q here, CQ. Yeah, so then I have this equation. Yeah, so let me now have a look at the solutions of this equation. And of course, I would be interested in the solutions with the eigenenergy equals 2 epsilon Fermi. That is the lowest possible energy for non-interacting particles in this strange situation, minus 2 delta. And I would be interested for the case whether I can have positive delta. That would mean that I would have a kind of bound state of these two particles. Bound state, in a sense, it has the energy below the continuum of non-interacting particles, below 2 epsilon Fermi. Yeah, that would be a real bound state, but in this very strange situation. Yeah? So let me plug it in here. Let me introduce a very famous notation. Yeah? It's exactly when you get this minus this. So then the equation would look like this. You have Cp equals minus G over 2. Yeah? This 2 will come out, G. Then you have 1 over psi P plus delta. That's what is left from here. And then you have sum over Q, CQ belonging to M, CQ. And this, of course, for P belonging to M as well. Yeah? So how can we solve this equation? We had it already for the zero sum. We have a similar equation. This is a number, so let's make on the left-hand side the same number. Let's sum over P belonging to M, both sides. So here we will have sum over P. Here we'll have sum over Q. We cancel this. So it leaves us to the equation 1 minus G equals minus G over 2. And I forgot somewhere, I lose the volume somewhere on the way. And then I will have volume, 1 of the volume, sum over P belonging to M, 1 over psi P plus delta. And this would be equation for my delta. Yeah, so therefore it's minus, or let me write now, modulus G divided by 2, integral over P belonging to M, dP, 2 pi h bar cube, and then 1 over psi P plus delta. That's my equation I have to solve for the delta. And of course, I will use, you see that M, this region, because this is very small, so it is just close to P Fermi. Yes?
Just before you erase it completely, so that I understand the potential properly. That the potential only means that if the particles have too high energy, they don't interact with each other.
If they have either too small energy, but below P Fermi they cannot be. If they have too high energy, they also do not interact. Yeah, this is very typical for the electron-phonon interaction. If you say about the atoms, this is a model things. For the atoms, we'll come back. We come back. Yeah, so of course we don't need these models, and then we have to be a bit more careful. But in the case of the metal, this is quite reasonable assumption. Yeah? And it allows you to solve the problem. So therefore, we have this condition. So therefore, P is very close to P Fermi. Yeah. So therefore, and in other things, of course, we're expecting the delta not to be very small. So we assume that there is this. Yeah, this we already assumed, but this is the delta is very small compared to omega 0. Yeah. So now I can integrate this in the same way. So I can just go to the integration over density of states, etc., etc. So this integral, okay, what we have 1 over modulus g, you have integral, then you have 4 pi, 2 pi h bar squared, then you have integral cube pf plus times these things, and then you have p squared dp, and now you have psi p plus delta. And of course, what you do, you write p squared dp, yeah, would be approximately p Fermi, then m p Fermi d on p squared over 2m minus epsilon Fermi. Yeah. This we know all things, the same tricks as before. D psi p. Yeah, so in the end, this and this combined into density of states at the Fermi surface, and then you have integral d psi p divided by psi p plus delta from 0, yeah, because so lower limit, to omega 0. And this is, of course, log. And of course, if I say this, I take just approximately nu Fermi log omega 0 to delta. And now comes a surprise. You always have a solution. Whatever small f is, because you see, again, we have g times nu f. And I forgot a factor of 2, I guess, right? I forgot a factor of 2. Yeah, you see this equation for delta always have a solution in the form delta equals omega 0 e to the minus 2 over f, where f is, as before, modulus g now, so f is positive, times nu Fermi. Density of states at the Fermi surface. You always have a solution. No matter how small f is, you always have a solution, contrary to the standard 3D situation. Yeah? Of course, this binding energy is exponentially small, but it is non-zero. Yeah? So you would expect, therefore, that motion of these two particles is correlated. So to break this coherent motion, you have to put some energy, 2 delta, in it. So this is kind of this bound state. This is not actually in the system. So in this case, it's really bound state for this very strange situation. But in fact, it's a coherent motion of these two particles together, and breaking this coherent motion costs you energy to delta. Yeah. You may ask me, yes, but you have some very strange, if not stupid, model. Yeah? Maybe it's just a model that makes it, yeah, and not the physics behind. Well, you can check that if you go to release this constraint, you make these states available. Yeah, let's see what happens. This means that I can continue up to here. Yeah, and then I also have to make assumption about my potential. Yeah, but let me make the similar model for my potential also in this case where all states are available. That all states are available means that I have to set this to 0 and this to 0. So now my energy range where I have attractive interaction not started from epsilon Fermi to epsilon Fermi plus omega 0, but from 0 to omega 0. Yeah? That would be similar assumption that we have here. So now if I continue this, yeah, so I plug it in here, I have my m is now, m becomes from m0 becomes now from 0 to square root of omega. Okay. Yes, so now I multiply. This is, I guess, 2m omega. 2m omega 0. Yeah. Would be like this, the range. Yeah, if I set epsilon P Fermi to 0. And just to save time, let me write down the results, what you get. Also assuming this condition. So you get exactly the same story. Yeah, so when Cp is non-zero only when the P belongs to these regions, but the integral would be different. Now let me write down the equation that you get in this case without, so you will have 1 equals 1/2, again, modulus g. Then you have 4 pi, that's our angular integral. And then we will have integral from 0 to 2m omega 0 p squared dp. And now 1 over p squared over 2m plus delta. Yeah, I just put epsilon Fermi to 0 everywhere. And I get exactly the same integral. So now under the assumption that delta much smaller than omega 0, yeah, the same part here, because we don't have epsilon Fermi, you can write for this integral the following answer. It is modulus g m square root of 2m omega 0 divided by 2 pi squared h bar cube. This looks like the density of states at energy omega 0. Yeah. And then you will have 1 minus pi over 2 square root of delta over omega 0. So if you now look at this expression carefully, you see that on the left-hand side you have 1. This bracket, if delta is non-zero, smaller than 1, yeah, therefore, for this equation to have a solution, this g times m square root of 2m omega 0 divided by 2 pi squared h bar cube has to be larger than 1. Otherwise, the solution doesn't exist. If it's less than 0, you have the product of two numbers which are less than 0, and here you have 1. You have a threshold. Like we should have. So in other words, interaction must be strong enough or broad enough in the energy space to form a similar kind of bound state, to form now the states with the energy which is minus 2 delta, less than 0 in this case. You need a threshold. So it's a standard result from quantum mechanics. So model is not so stupid. At least it reproduces the famous result for two particles in vacuum. Yeah? But if you add the block part of the motional space, you block them here, saying, okay, this is my Fermi statistics. Huh? You cannot go here because states are occupied. You get a correlated or bound states of two particles. Of course, in reality, things are a bit more complicated because it's the same particles. Huh? It must be identical to these two, because otherwise, for non-identical particles, there is no exclusion principle. Yeah? So it must be the same particle. You can ask what, if, how it can be. So, okay. But in principle, you can continue. You can make a bit more clever. You can say, so here we have two particles on top of the frozen Fermi sea. You can say, let me take two excitations, particle or hole, that can move. Yeah? But interaction, again, in this strange form, then you can get one here. Yeah, but it doesn't matter. So you see, in this simple model, reproduces the exponential form of the bound state, and we will see that will be exactly the same for the critical temperature when this too happens, when the electrons not anymore behave as individual ones or fermions, individual quasi-particles, but they bound in these coherent states. Yeah, and then later on we will see what kind of a strange coherent states. I especially don't like to say a bound state, because for bound states we typically think that the size it should be smaller than the separation between the bound states, yeah? Because otherwise that's kind of very strange things, yeah? And it would be the case in this, yeah?
So with the impulses exactly opposite of each other,
Yeah.
isn't that very restrictive actually?
Or you can have a look at the, it's a good exercise, you can have a look when the center of mass is non-zero, and then you will see there would be critical value of this center of mass motion belonging to you don't have this state. You will have that with the p, this delta decreases, and at some point disappears.
The second thing, if they're moving in opposite direction, how can they be bound? Or is it like an oscillation kind of thing?
Oh, sorry. It's actually it's a whole combination of how they go. In a sense, this is not the true bound state, yeah, which you have. It's actually. I will write down you the wave function, and then you will see. So if you go to a different regime where interaction really strong, it's called BC to BCS crossover. Yeah, you start with BCS regime, which is here, which is kind of Cooper pairs, which you shouldn't think in terms of bound states. So you shouldn't think. You will see that the correlation decays exponentially, nevertheless. But if you go to the other regime where interaction is strong, and you can form the bound state of two particles in vacuum, yeah, then of course you go to the case where you have these two particles molecules moving around, and it's actually you can see how the wave function goes from BCS form to the collection, to the BEC of these molecules. And then indeed you will find the wave function of that form in a momentum space. So it's a radial wave function, will be controlled by Yukawa. It has a Yukawa form. Yeah, then they're really found, but also if you expand the molecular function in the Fourier component in the center of mass, you always have p minus p. Yeah, so you can ask the same question and try to answer it for the case of molecules. So it's not necessarily p and minus p create an extended state. A proper combination can create for you exponentially localized state. It's just a matter of how you add them. What are the coefficients? Okay, so now we're coming back to the real situation where you have this Hamiltonian sum over p sigma epsilon p minus mu. Yeah, I subtract mu n, ap sigma, and now so now I have to, okay, plus, let me write down in this form dr, and now I will have psi dagger plus r, psi minus r, dagger psi minus r, and psi plus r. This is our Hamiltonian. Especially don't write in momentum. I can write in momentum space, but maybe this consideration would be simpler. And then you see that all these, so p minus p, they all, it's sort of a superposition of the state, which we form in a wave function. You have many such correlated states for each p. So therefore, it's very natural to think that there appears some mean field object. Let me write it like this. G, 1 over volume, sum over p. So you have to a new state, which is formed by these correlated pairs of fermions that move in together, break in which you need an energy 2 delta. So with this, this G, this bracket is a new unknown ground state, or what you have at finite temperature, some density matrix or thermal density matrix. I don't want to specify it now. We can have a ground state, or at some point we will go to a finite temperature. We will need the gap equation. But so you form this, and this is non-zero. Yeah, The question is, of course, we should find indeed the condition when it is possible. But you see, it's again, that's what happened. I remove here particles of the opposite side, of the opposite species, which will interact and have opposite momenta. So I just remove such pairs, yeah, but because there are so many of them, it's just like in a BC. So you roughly have BC of these pairs, yeah, and then you just remove the pair, and therefore the average does not change. Yeah? Just this operator, it becomes a C number. Because there are so many of them, just a C number. Yeah? And this means is actually in the language, it is this one. Exercise show this. And of course, it's based on the fact that if I have, just a hint, if this state doesn't have momenta, as we always assume, that the average minus P minus Q minus an A P plus Q P1, P1, P2, Q plus is just only non-zero, only if, or you can write it like this, maybe it's easier. Yeah, because that's what you would have this term. Only non-zero if P1 equals P2. Because otherwise this operator takes some momentum or adds some momentum, and the state with this momentum cannot have overlap with the initial state that doesn't carry any momentum. So we use this form in a different way many, many times. Yeah. So now we assume that this happens like this. So we have to therefore simplify our Hamiltonian in more or less the same way as we did for bosons, with of course some difference, because now the pair of operators gets an average value. Not a single operator, remember A0. So here we have pair operators, but it doesn't make a lot of difference. Yeah. So you can just, using this, you can write this Hamiltonian in the following form: P sigma, epsilon P minus mu, A P sigma, dega A P sigma. And now, of course, in the ground state, we also assume that if I do the same for the dega operators, yeah, I can do this A P plus dega A minus P minus. Yeah, that also should be 0. And let me assume in a simplest case that it is equal to delta. Yeah. So just in the ground state, this is not a bad assumption when you have no flow, because if it has a phase, this is gauge variant operator. I can put the phase on this operator. I can redefine new operators A, which carry the half of the phase of delta, and delta, and all disappears. Because this is gauge variant terms, so this appearance of these averages breaks the U1 gauge symmetry, yeah, in the system. Yeah. So now what we have, we just, you see, once I replace this one with delta star, which is delta, and the second one I replace this one pair with delta. Yeah, so what I get here, I will get plus delta integral dr, and then once I will have psi plus dega r psi minus dega r plus psi minus r psi plus r. And then, of course, to be, okay, you have to subtract some constants, something like minus volume times delta squared over g. Yeah, but we ignore this. Yeah, because if it's important.
In delta star, it is A dagger.
Oh, sorry. Yes. A dagger. Yeah. So it's the same gauge variant operator. A dagger A is gauge invariant, but this, yeah. So also you may ask me why you don't introduce the average of these things, which is just a density. Yeah. All these things of minus or density like this, which is a density of the plus component. You will be absolutely right. Yes, in principle, you can do this, and you should do this. if you want to be more fair than I. Yeah. But then you see what happens. Then you get delta R, some constant density, psi dagger psi. So this simply adds to the chemical potential, like what we had already in the first order, Gn. So this you can introduce, but it does not change physics. They simply, these averages, these ones, redefine the chemical potential for minus particles by adding Gn, for plus particle by adding Gn minus, and this average redefine the chemical potential for minus particles just adding Gn plus. Yeah? But the Hamiltonian doesn't change. This is more drastic things, because if I rewrite this Hamiltonian in a second quantization, the second term, what I get would be the following. Sum over P, and then I will have, let me call this psi P. This is a very standard notations for fermions. So it's psi P epsilon P sigma deg, AP sigma. AP sigma, this is my kinetic part, plus delta, and then you will see the following. You will find the bracket of AP plus dagger A minus P minus dagger plus A minus P minus AP plus. And again, plus some terms which I'm not writing. You need them. You will need them if you want to calculate the ground state energy, which in the end you should do, of course, to show that the new phase that you get has a low energy and not some metastable high energy state that you artificially create. You have to do it, but believe me, the energy would be negative. Yeah? So making this delta will decrease the energy. Yeah? So now we have this Hamiltonian to diagonalize, which looks like very much like the BEC for bosons, but now we have fermionic operator. Before I come into the Boogaloos transformation, which I will, of course, use in this case, let me tell you a bit more about the approximation behind these things. Yeah? We have this part in the Hamiltonian. Let me erase this. And this is a key equation that would actually we will use to show that the delta is non-zero. Yeah? Because it's all at the moment nice if I assume the delta is non-zero, but I have to show this. It's indeed non-zero. Yeah? But before I going, let me show some what's the physics simplification behind this BCS model. Remember, we have this Hamiltonian. It has the following form: G over V. If I go to second quantization here, we have P1, P2, Q. And then we have AP1 plus Q plus particle dagger, AP2 minus Q minus particle dagger, and we have AP2 minus AP2 plus. Yeah. So if you compare with this one and this one, yeah, and if you think a bit, so you will understand that actually what I can do going from here to there, if I ignore all the collisions between P1. Yeah. So I keep only collisions, you see, because here I will have P2 equals to minus P1. Yeah, that's the term that I have here. So this and this momenta are opposite. Yeah, but in this form they can be arbitrary. Yeah. So therefore, to have the BCS model in this form is equivalent that I only keep collisions that lead to the opposite momenta. So yeah, this is called BCS Hamiltonian. Sorry, not saying this. So in the BCS Hamiltonian, this you replace by G over V, sum over P1 and P2, A P2 plus dagger A minus P2 minus dagger, A P1 minus A P1 minus, A P1 plus. So in this model, you allow only collisions between particles with the opposite momenta. You see? P1 minus P1, P2 minus P2. Remember, it was very much, so therefore, this term exactly in the BEC case takes the following process: particle with opposite momenta collide and go to this collective mode delta, or they appear from this collective mode delta. But there is no collisions between particles with a non-zero total momenta. Yeah? So it's very much similar. So therefore, you cannot directly apply this result to the gas, because in the gas you have also other collisions, and I will show you what would be the difference, yeah? Yeah, for the gas and for this BCS model. Yeah? So of course then you see you have two independent sums, and one of them you can just split by Haber-Satanovich and whatever, and then this is completely equivalent to what I said here. If you replace this Hamiltonian with this one, it's similar to BCS model. Yeah. So how can we solve them? You are experienced already. We use Boogaloos transformation. So here we have extra index, plus or minus, and they look like this. Of course, you want to introduce new operators AP plus, which is UP AP plus VP A minus P minus dagger in this form. But alpha P minus, after some struggle, you will recognize that you will have to put here minus. So for plus you have plus, for minus you have minus. So what you can write in a more general form, alpha P sigma is UP AP sigma plus sigma VP A minus P minus sigma dagger. So this is kind of a general form. And of course we want that this operator be fermionic ones, yeah, because it's linear combination. And we know that we want alpha P1 sigma 1 anti-commutate with alpha dagger P2 sigma 2 would be non-zero if P1 equals P2 and sigma 1 equals sigma 2. And all the others, alpha alpha, let me write it like this, and alpha dagger are 0. Again, as in the case of bosons, I don't consider this, I can consider this real. And depending only on the modulus, that would be sufficient to describe the ground state, not the state with the superfluid flow. Yeah, but for the ground state, that will be completely sufficient. So you can very easily put a dagger, and then here dagger, and dagger disappears for the dagger operator. So now, if you do check what conditions for U and V you need, yeah, to get this one, you will find out that you will need from here. Remember, for bosons we will have, okay, so let me no. The conditions you would be UP squared plus VP squared equals 1. For bosons, we get a minus here because commutator A with A dagger is minus commutator with A dagger A. Yeah, and that was a minus. For fermions, it's anti-commutator, so it doesn't matter. A dagger or A dagger A, the order doesn't matter. So you get, therefore, you don't get this extra minus sign. You get this one, and it looks like UP is cos phi P, and VP is sinus phi P. So I write it again so you can very easily find inverse. Yeah, and inverse transformation is AP sigma is UP alpha P sigma minus, yeah, because V changes sign, minus sigma VP alpha minus P minus sigma dagger. That's the inverse transformation. And then we know what to do. We just put it in this Hamiltonian, do some algebra. Don't forget operators are fermionic. Yeah, and what you get, so the idea is now we put it there, and we want that our Hamiltonian goes into the form E0, like in the case of bosons, plus sum over P sigma some positive energies EP, yeah, alpha p sigma dagger alpha p sigma. That's what we want. We diagonalize this Hamiltonian. Yeah? That's our wish. That's what we want to have with EP positive or 0. Yeah? And I wouldn't do this algebra that I did for bosons. I hope you understand why. So you get an extra condition such that no alpha alpha and alpha dagger terms, that gives you that the very similar conditions actually like for the bosons. Yeah? Very, very much similar. 2 psi p up vp equals delta up squared minus vp squared. Unfortunately, they always come here with the wrong sign. Yes, it's not. For boson it was a plus and the minus. For fermions, opposite. Yeah? And I give you now the solution. So we have this, and again this. Yeah? For each p, 2 unknowns, 2 equations, you have to choose the right branch because it squares. Yeah? And what you get is the following solution. up squared is very similar. 1/2 1 plus psi p divided by EP. up squared is 1/2 1 minus psi p divided by EP, and EP equals square root of delta squared plus psi p squared. That's what you get by solving this equation, system of equation. Looks very much, yeah? So now let's check. We already know the limiting case. We know delta goes to 0. Yeah? EP would be modulus psi p. Yeah? Remember, ideal Fermi gas, excitations. Modulus psi p. UP, this would be signum, yeah, which would be only non-zero above P Fermi, and then you have 1. So it's step function P minus P Fermi, and VP would be opposite step function theta P Fermi minus P. Remember, I diagonalized for you the Hamiltonian of 3 fermions. Yeah, we get exactly this, so we choose the right branch here. But now let's have a look at this, how it looks like, and then you recover a very interesting feature. Yeah, this is P, this is something P Fermi, where this is 0, and this is a P. How it looks like. Remember, in the ideal Fermi gas, we have it like this. Yeah, that was ideal Fermi gas. This is modulus psi p, yeah, the dashed line. And now when psi p is 0, where these touches for ideal gas touches 0, so here we have delta. So it looks like this. So you open a gap for single particle excitations. So that means when you form these correlated states, yeah, you cannot move one particle without touching another. In order to move one particle, you have to break these correlated states with another one. So therefore, this water that we have for the ideal Fermi gas, this analog of the Fermi C with a very fragile, so now it covers, you will see, with a thin layer of ice. So to get the water out, you have to break the ice. That costs you energy. Yeah, so now we have gapped spectrum. Gapped single particle excitations. Actually, to create a particle Hall pair, you need a gap 2 delta. So therefore, superconductors are transparent for infrared light because it not have enough photon, has not enough energy to create particle Hall excitation. That's exactly for this reason. Yeah. If I calculate, of course, here I assume that we will see that it's indeed the case. Yeah, we know already this delta has to have some exponent in it. Yeah, exponentially small. Yeah, if I look at the range of momenta, where the dispersion is affected by this delta compared to the dashed line. So this delta P would be such that I have delta divided by V Fermi. Yeah. This is approximately this range, yeah? Because this is exactly where my dashed line, which is modulus psi, near the Fermi surface, V Fermi P minus P Fermi, yeah? So this V Fermi delta P is of the order delta. That's exactly the size of this region. It's this one. And now, if I calculate what this delta P corresponds to distance, which distance, yeah? This psi, this is coherent length again. Which is h bar divided by delta P. Yeah? Then you will get the following. It's h bar V Fermi divided by delta, different delta, this delta. So now let me do the following. H bar divided by P Fermi, and that is my interparticle separation, average interparticle separation, times P Fermi V Fermi divided by delta. This is of the order of epsilon Fermi. Yeah? It's half, twice. No? So then what you get is this psi. Let me specially write it somewhere. No, just continue. The psi is average interparticle separation times a very large number, exponentially large number, epsilon Fermi divided by delta. This thing is much larger than 1. So therefore, the size of these correlations exceeds exponentially larger compared to the interparticle separation. So it's not a molecules, yeah? Because what is the molecules? It's so overlap with each other, so it's a kind of soup, but not, yeah. So it's really correlated states of two particles. Yeah? They are not real bound states. They simply move in a correlated way. Don't talk about the real bound states. Sometimes people call quasi-bound states, but it's saying that it's not a bound state. It's a different way of saying this. Yeah? So this is much, much larger than h bar over P Fermi. And this is actually, for those who knows, it's actually very good for the mean field. Yeah? So the mean field description that we're having here, it's a very exact for weakly coupling superconductors. Although it's a second order phase transition, but the mean field description is extremely exact because fluctuation region is extremely small, but this maybe will come in a few minutes because it's all nice what I said, provided delta is non-zero. Yeah? Provided delta is non-zero. So how can we know this? Yeah, we have to go back to the definition. Let me just use this formula and erase them by the time I don't need them. Remember our definition. It is G over V, sum over P, and then we have this A minus P minus A P plus, and now average. Yeah? So in principle, in average, if I sit in a T0, I have my ground state, which is defined in the following way. For all alpha P sigma, it has no excitations. Yeah? Remember, the same definition as for bosons. And here, let me write you down the exact expression for this ground state. It is product over all P less than P Fermi, UP plus VP A minus P minus A P plus dagger acting on a vacuum state. So you see, you populate with pairs minus P, P minus P, P. Yeah, and you see, if you go to the ideal Fermi situation, delta is 0, you exactly populate inside the Fermi surface when V is 1, and outside would be empty. Yeah? And this is a nice function because it can be used to describe crossover. Yeah, but if you add finite T, of course you start creating excitations. Yeah? N alpha on P would be given the fermionic excitations. Yeah. You will be given by the Fermi-Dirac distribution. You have an average number of excitations that you create. Of course, at small temperature will be very exponentially small, yeah, because you have activation, you have delta, yeah, but it's what like this. Yeah. So now how can we look at this? This is our definition of delta, but now we know that A's, how we do it, we express in terms of alpha and calculate this average using either this ground state or the definition of the thermal state. And this gives me the following thing. Let me just continue here. I will not do this algebra. This is straightforward, but I don't have time. I have only 5 plus 5, 10 minutes. So equation that I get, I write it for finite t. Equation what I get would be the following. I will have minus g integral, let me just use it, okay, dp over 2 pi h bar cube, and then you will have tangent hyperbolic ep over 2t divided by 2 ep times delta. So this would contain upvp and then some that comes from occupation number of excitations. 1 minus 2 np alpha would be like this. And if you do some algebra with this Dirac form, Fermi-Dirac distribution, you get to this tangent. And now we have equation, yeah, delta, delta. Of course, delta 0 is always the solution, yeah, but it's trivial one. So we want for the non-trivial one, where here we just have 1, and here we have 1. Yeah, assuming that delta non-zero, that's the most interesting case. Yeah, we're looking for. And this solution has the name, it's a gap equation. Gap equation. But unfortunately, it has the same problem as the, remember we calculated ground state energy of the superfluid Bose gas. Yeah? So if you look at a large momentum, it diverges. At a large momenta, EP becomes p squared over 2m. This is 1. Tangent hyperbolic goes to 1. And this becomes p squared over m. So if you look at a large momenta, you recognize here the same problem as we had for bosons, because you have this integral. Diverges at a large momentum. But we cue this thickness using the same procedure. Remember, we had at that time for bosons, we had a very nice equation for the scattering off diagonal, off shell scattering amplitude, which we considered E equals 0. Then this gamma E p prime will go into 4 pi h bar squared over 2m over m times the scattering amplitude. Yeah. And equation that we have, remember we have gamma equals v tilde plus integral, I write schematically, dq 2 pi h bar cube. So now E is 0, so we have minus q squared over m plus I0, which is irrelevant, but here we have v tilde, and here we have gamma. The equation looks like this. So let's now apply the same model for the potential contact that we have in this Hamiltonian. So therefore, we just replace this with g. So here we get, let's say, minus. So here we have m over q squared. And then you will very easily see that in this case, g and gamma, so maybe I write it, becomes momentum independent. So you get it like this. And now if I divide by g gamma, so I get 1 over g equals 1 over gamma minus this integral. And if I divide by g here, I get this one. under the same assumption. So in principle, I should say I integrate here over some lambda, which is of the order of the inverse size of my potential. So here I should also say I integrate over same lambda, which is of the order inverse size of my potential, if I want to be a bit more rigorous. Yeah? Of course, it's not a mathematical. But now if I put this in there, you see, in there, and if I do some manipulations, very simple one, equation which I get would be the following: 1 over gamma, which is m over 4 pi h bar squared 1 over a, sorry, this looks like q, this is a, equals, now we'll have integral dp over 2 pi h bar cube, and then we will have tangent p over 2t divided by 2ep minus m over p squared. And now this is convergent. And a minus I need here, I guess. Yes. Yes. So this would be, this is a gap equation which is completely mathematically okay. Yeah. So all the integral is defined, so you can find. So now I have a few minutes to present you solutions for this equation. Delta is non-zero for t below Tc. So you will find out that you need a Tc below, temperature below some value in order this equation to have a solution. And this Tc is equal, there is some number, gamma is the Euler constant over pi, 8 e to the minus 2 e to the minus 1 over f, where f here is our familiar f. Yeah. 2, now modulus A, P Fermi over pi h bar. So it's positive, but very small. Yeah? So you see you have an epsilon Fermi, I forgot. Epsilon Fermi sets the scale, but it's exponentially smaller than the epsilon Fermi. So indeed, delta is exponentially smaller than the Fermi energy. Yeah. And if I look how this delta depends on temperature, you will get the form like this, where delta 0 is always related to Tc by some universal relation, pi e to the minus gamma Tc. This is a mean field relation. So whatever you do in mean field, you always have it like this. And here, of course, as in a mean field, it goes like Tc minus t divided by Tc. And the overall coefficient is scale is Tc. So it's a square root behavior. It's very typical for mean field solutions, yeah, which are very nice here. And but this is BCS. Now, if you want, as I said, it's only collisions of particles with total momenta 0. If you want to take into account all collisions, yeah, then you get slightly different answer. Tc in the gas. In the gas means I take into account all collisions which are present. You get slightly different answer. Ah, yeah, and this coefficient is 0.61. Yeah, it's just a numbers, universal numbers, 0.61. Just in the more honest approach, you get slightly different e to the gamma over pi, but instead of this, you get 2 over e. It's famous e 7/3 epsilon Fermi e to the minus 1 over f. And this number is actually a bit smaller, twice practically. So you see, if you take into account all other collisions, they work destructively on the pairing. Yeah? But anyway, in both of the cases, below Tc, you have some delta, non-zero. You have a gap single particle excitations. Of course, in this case, this is a critical velocity if you calculate according to divided by P Fermi. According to Landau criteria, it's of the order of delta divided by P Fermi. Yeah, it is non-zero, so you can expect the superfluidity. Of course, in this case, you would also have a collective modes. I'm already beyond my plus first minutes. Yeah, but let me say a few words. We have a collective mode which is actually sits in the phase of my order parameter. Yeah, it's a Noether theorem, if you like. Yeah? I break the gauge invariance by introducing delta, but the small fluctuation of the phase give me the order, give me the collective mode. This is Bogolyubov-Anderson sound. Bogolyubov-Anderson, although Anderson considered this, it's not for electron system sound. This omega equals C times K, the dispersion. But funny things, if you calculate this, C in this case would be very close to V Fermi divided by square root of 3, like what you have in ideal gas in the thermodynamics, although it's nothing to do with thermodynamic things. Of course, I can say more about this state. There is a very interesting physics, but the only thing I mentioned is that if I now calculate the number of particles, the distribution, yeah? So it's AP sigma dega AP sigma, let's say 0 temperature. Yeah? For the ideal gas, we have a step, but these things would be like this. This is actually, as for the bosons, for T0, it's Vp squared. It's the same, like for the bosons. And non-zero, you get some extra temperature dependence contribution, and it's look like this. It's a smooth crossover around P Fermi. So this is actually Vp squared. And if on the same plot I plot Up squared, which is 1 minus Vp squared, you get like this. This was Up squared. But Vp squared has a meaning of a momentum distribution of initial fermions. So you see it's smooth, no step functions. No? But this smoothness is kind of nevertheless provide the rigidity delta to single particle motion. Yeah? Which gives you superfluidity because again, this we know, this dispersion, linear dispersion does not violate the Landau criterion. Here is single particle excitation. We also get some non-zero value for the critical velocity. To this system, attractive Fermi gas is superfluid below Tc. Yeah. I think I should stop, yeah, because there's anyway too much to say in this time and make no sense. Yeah. Okay, so thank you for your attention. Mm-hmm.
The last point about reciprocity was not clear to me. Is it necessary to consider additional collision channels to get superfluid or from...
Sorry, I didn't understand the question.
Is it indeed necessary to consider additional collision channels like in the last part of unit 2 to get us like superfluid, like according to the Landau criteria, or does it follow the
Landau criteria. In Landau criterion, you have to look at the minimum epsilon EP divided by P for all branches of excitations. Because in principle, you can create whatever excitations you have in the system. In this case, particle hole excitations or collective mode. And in both cases, you know you can apply this, and in both for these both branches, the minimum value is non-zero. Of course, it could be like in what is real critical velocity in this case. It's a bit a subtle question for the reason because it's also subtle for helium-4. It's not the phonons that limits by the VC critical velocity, but it's a vortex rings. So you really have to be, which are topological excitations. Vortex ring has some. So here you also have rings, so you have to be very careful what is actually limiting your critical velocity.